Hello. Can you hear me right? Oh, thank you, Collins. So let me share my screen. Chat box. All right, so. Welcome to week 12, lecture A. Starting from today, we are going to study digital controls. And many people had a wrong impression that if I know continuous time control like we have learned so far, why we still need to learn digital control? This is a question we need to answer in this module. So we're going to use this week, maybe half of next week to study that. So let's get started. So the key references are Ginny Franklin's Digital Control Dynamic Systems. This is a very nice textbook. It's considered as a Bible, okay, of digital control, okay. When I was working in Seagate is a manufacturer of the hard disk drives. I worked there from 1999 to 2000, 1.5 years in Seagate doing the disk drive control. Everybody has a copy of this book, okay? There's another book, it's called Digital Control by Phillips. Also a very good book. So what is digital control? What are the tools? Anything special? In practice, what are the issues? So we need to answer these questions. So this is an outline that I ask you also put into your quiz, okay? So first, feedback control and talking about difference equation. Remember, we are not talking about differential equation, we're talking about difference equation and its solution. Then we know that for differential equation, we do a Laplace transform. We can convert that one into algebraic equation. Then we can solve differential equation by using Laplace transform. There's something parallel, it's called Z transform that we are going to learn. Another thing is regarding a Powell's transfer function. Remember, you have a system, you have a signal going through a system. Then you have y of t. So this is a system, LTI system, linear time invariant. And its impulse response is g of t, which is actually inverse Laplace transform of g of s. So then if I have the g of t, then my y of t for any given u of t, then it's convoluted with g of t, okay? And in Laplace transform domain is y of s is g of s times u of s. So all these are continuous time domain things. Another important factor is regarding sampling. We are going to have a very deep studying about sampling. What's the consequence of bad sampling, okay? If there are good sampling, there are bad sampling, okay? And how we can connect continuous time and discrete time and poles and zeros and so on and so forth. In particular, a practical way is called a discrete equivalence. We are going to learn that. Okay, there are also ZOH, zeroth order holder. Okay, so control, why we need a control? Okay, the control is we are going to make the system to behave as what we want. Okay, so because we have some uncertainties in the system, we need to overcome. Okay, and so unsure of the signals we are getting, and feedback control help us of overcoming of those uncertainties. So in fact, the feedback control is to attack those uncertainties. If everything is crisply known, Okay, if you know that I want my system Y to behave like R, okay, so it's easy. You just put the inverse of this one, open loop. You put R in here, then you get Y equals R, right? So this open loop will, so then you need to precisely know what is your G. So that's not practical. You don't have 100% knowledge about the G of S. You only have a rough model, okay? That's why we need feedback control to deal with these uncertainties, okay? And perhaps external disturbances. So say, for example, you have some disturbance in here, the feedback will help us to overcome that. So the tools, as I said, use MATLAB Simulator a lot, okay? And most recently, I think you probably are among the first in the world in a classroom setting like this, learning a digital twin, okay? And now you are learning how to create a digital twin yourself. So I feel proud of you all that being able to accept the digital twin. And the digital twin is the foundation for our next wave of industrialization. It's called Industry 4.0, okay? Industry 4.0. And in common languages, people talk about this one as digital transformation. So this is still a ongoing process about digital transformation today. We're in the middle of this. So objectives of control, you know that first thing first, being stable, okay? If your input is finite, your output should also be finite, okay? BIBO, stability. And also you need a zero steady state tracking error. Your ESS is 0. Is actually E to the infinity is 0. And you need disturbance rejection and also a good transient as fast rise time, overshoot is small. All these could be conflicting, okay? So this is actually, so in that sense, the control, you have your way to choose it. So control sometimes is also called the art of trade-off, okay? Art of trade-off. You cannot be too fast, then you will be closer to being unstable and so on and so forth. How we do that? So we're still using the principle of MAD. So you need to have a certain level of knowledge about your model, then make analysis, specify your specifications, then you design your controllers, okay? So start with a model, decide on the control specs. What is the control architecture? Structure is also architecture. P, PI, PID, lead-lag, and other method. I taught you last time, we called IMC. Because of internal model principle, say for example, you have sinusoid as an input. So your controller should contain this in your, so this is sine T, okay? So you should have this term in the denominator of your controller to make sure you can have zero tracking error, okay? So that's internal model principle. It is a generalization of the concept of system types, okay? You have learned a system type 1, type 0, system types, okay? Type 2 system, so. Then decide the parameter like PID, you have a Zyklon equals tuning row, Cohen cone tuning row, and so on and so forth. Then you double check whether you actually verify whether you can satisfy all those specifications. If not, you do again, okay? Then finally, it's the digital, is usually digital, okay? It's usually digital implementation for control system using a microprocessor or controller. Okay, so so this is a traditional analog feedback control. So everything here is continuous time, so analog, okay? Plant, control, disturbance, set point, output. So this is your control signal, this is an arrow signal, this is a negative feedback. So that is our familiar form in continuous traditional feedback control loop. So for the computer control, you have to convert the analog measurements into digital form. So it's called analog to digital converter. C is a converter. So analog to digital converter. Okay. And then after you made the decisions in here, then you need to turn this digital signal to analog. So DAC, DAC. You can see ADC and DAC. Then this is a control signal, usually is analog, okay? So here you have an analog as well from the plant, okay? So that loop, I hope the key difference is everything here is digital, okay? Everything here is digital. So you have digital, analog to digital converter, then digital to analog converter. You need these two converters. The basic principles of ADC and DAC are already in our textbook. You can read the basic principles behind. But today you can just buy a chip. It's highly integrated, okay? So control in a continuous time domain is CT domain. This is discrete time domain, okay, digital. So the differences is you have, this is like analog, this is a digital, this is a digital, this is a digital. This is also digital, but now with zeros order holder, this is analog. So analog, this is a DAC, this is ADC, analog to digital controller. So this thing actually is called sampler, okay? Sampler. This sampling, sampling of this continuous signals. We're going to explain that. So three key questions for this is in the quiz, okay? How fast we should sample? We need to follow the sampling theorem. So I'm mentoring two capstone teams. They do not know the sampling theorem. Then how you can choose your ADC chip, okay? ADC chip. So you need to do those basic decisions about how fast we should sample. So how we represent the relationship between input and output in the discrete time domain. Basically, we have a difference equation, then doing a Z transform. And we'll talk about discrete time convolution with impulse transfer function. Then after that, how we can design using these models in the digital domain. So how we can design. So that will be the last part of this course, okay? So that my discrete controller is equivalent to my continuous time controller, okay? So in this one, we are going to learn, digital equivalent of the continuous time version, okay, for the control design. And we're going to learn something parallel to Laplace transform. It's called a Z transform. And we are going to have a homework on this Z transform part, some basic properties, and S and Z domain, what's the relationship? Okay. All right, so in the end of the course, you should be able to understand, in the end of this module, you should be able to understand the sampling issues with their implications. That means if you do a bad work in choosing the sampling period, or your sampler are not fast enough, what's the consequence? Should be able to implement a continuous time design and understand the problems involved and properties of digital system. You also should be able to design directly in the digital domain. Okay. So now let's switch to difference equation. Okay, difference equation. So let's talk about lecture hall or conference room. Okay, for temperature control. Okay. So the stable means you have temperature more or less the same. You don't want to go like suddenly very hot and then very cold, very hot. This kind of thing is no good. Okay, no cycling between those extremes. And it's accurate, meaning if I want 70 degrees Fahrenheit, it should be around this. Better to have no steady state error. And if I want to change, it should be changed fast. It's called transient. The response should be fast. Robust means, so if you have different number of people in the room, then your heat capacity is different, okay? Because everybody is a heater, okay? So then your system behavior should not be influenced by this. We call this is a robustness to the load, so heat load to the load. So you cannot say that you have a bus. If full of people, the bus behave very strange, or no people there is another behavior. So they should be consistent, meaning kind of robust in the performance. So this is a visual illustration about what do we mean transient. So the transient can be slow or can be large, okay? When you have a slow transient, a slow overshoot, then, smaller overshoot, then it's a slow response. So if you want a little bit faster, yes, you can, but you probably at a price like this. Okay, so this is a higher overshoot. But you want to say some sluggish one, so you can do very slow like this. Make sense? So there's a trade-off depending on what do you really want. And I say the robustness. I say the robustness to disturbance, like number of people in a room for the room temperature control, or environmental, it's a hot day or cool day, and so on and so forth. On the other hand, there's also uncertainties in modeling. Your model may not be accurate. So you say, oh, I use this model, but everything, all models are wrong. Some of them are useful. So this one is useful to design PID control using Zaghloul-Nichols tuning rule. But this probably is close to the truth model, but there's still a gap, okay? So whether my controller design can tolerate this kind of gap, this gap is model uncertainty. It's actually called model uncertainty. Okay. And perhaps you have sometimes the sensor contact is a problem, some sort of partial failure. It can still work, okay? So that's another side. Yeah, actually, there's a dedicated topic. It's called fault tolerant control. So even you got some fault, I still can keep things under control. Okay, so now let's take a look of the model. Okay, so we have heat coming through the vent and heat removal. Okay, so the room temperature is the variable we want to control. So heat coming, you have A stands for ambient. It's an environmental and temperature, surrounding environment, external ambient temperature. A stands that. So this is a in. This is a heat removed. Should be the proportional to, this is a heat capacity constant. So d theta dt. So that's the first order differential equation, as you can see, right? And in here, the Q is something as a controller. Okay, so this is the controller input. So say, for example, you have air conditioning. So in the continuous time domain, it's very simple. And this is my output. This is my input. This is my output. And this is actually my transient, my ambient disturbance. Okay, disturbance. So my point is, can I measure the theta and choose some sort of controller and give a set point here. So I do this type of negative feedback so that my output is maintained at the set point, okay? So that's the control task, okay? And I think at this point, you should know that this is a type 0, right? It's a type 0 system. So that depends on what you put into the controller. If I put a KP here, you immediately can say that the steady state error is not 0. Because in here, you have set point is a constant, then it's a 1 over S. So this S is what I call the generator of the signal. And this is not contained in a loop transfer function. So therefore, it's not satisfying the internal model principle. Therefore, the steady state error is not 0. You can prove it. So here's the way we can show. Very simple, okay? We'll put the KP here, okay? So let's try to do our math, okay? So this is my controller law. That's controller law, meaning I'm measuring the set point minus my theta. This is a minus. So this is also called E of t. So this is actually a E of t, and times the gain Kp. So here we use a kappa, okay? This is my K. So that is my controller. I put this controller in. So this is my Q is this one, and put this one in here. So then what I get is kappa and set point. This is my E. So this is not, this is just ambient temperature and my real temperature difference. So I do, I remove, I can lump the theta term. So I have a capital K and the kappa, and here I have a set point, I have ambient, okay? So this is the first order differential equation. These are external input and set point, okay? By doing that, there's a one way to do the steady state characteristic. So first of all, when we say steady state, it means everything is settled. So anything, then the derivative will be 0 in the steady state. Make sense? So in the steady state, this guy is 0. Okay, so then we just leave these terms alone. So then the theta will be divided by this term, both sides. You are going to have this term and this term. So you are going to see that theta will not be the theta set point. It is not. There's always an offset. Okay, so we proved that using our internal model principle. Okay. So also, we don't have the robustness to the disturbance at the steady state as well. But if my controller gain K is big, if my controller gain is really big, so then this thing will close to 1 and this thing close to 0. So this is in a limit case. But can you really put the KE is a U? Can you kappa E times E? Can you really put the kappa to a very big number? The answer is no, don't do that. The reason is, remember, you also have some noise in your measurement, okay? So this noise will also get amplified a lot. So then your actuator is constantly switching, okay? High and low, high and low. So that is no good. That is no good. So if kappa is very large, then time constant is very big. So you push your kappa is big, you will have this. Okay. So the high gain give us faster response, better accuracy. Why not use a very large gain? I already explained the noise. Okay, the noise. So very small change in theta. Say for example, theta is your measurement plus something noise, epsilon. So the noise measurement will be amplified a lot. Okay, you will damage your air conditioning very easily. Okay. So the system may approach to an instability. So maybe we'll also have some small delays in our plant. So end up with a high unstable system if your kappa is too big. Okay. All right. So here is the same. If you have some changes in here, noise, this is like changes. Then your control signal will also change very big. Then that will make your actuator to act so often that soon it will get worn out or you need to replace it. So that's not desirable. So then, of course, you need to think about using an integration PI controller in this case. That's a different story. We want to now discuss a parallel discrete version of it, a digital version. So again, you have a room temperature control system. So again, this is analog. This is analog. Okay, this is analog. This is analog, meaning continuous time signal. But they have sampler here with a sampling period is TS. So this is digital. Okay, this is also digital. Okay, so then until you get through the 0H, here it becomes continuous again. So okay. So the system, the input to this plant only updated at the sampling instance. Okay, the 0H is like, so you have those control instance. Okay, after the kappa, the control signal in here is something like this. Okay, but after 0H, it will become something like this. You hold it until the next one. Hold it. So this is called 0H, a zeroth order holder. Zeroth order means straight line constant. It's a piecewise constant. Okay, so then you hold it. Okay, so this is a hardware mechanism. Okay, in the DAC system. Okay, all right. So otherwise, you are going to hit the system with all these pauses. That's not right. Okay, so let's starting from here. This is a continuous time domain. But let's do DDT like we learn about T plus TS divided by TS. So this is called rectangular approximation of the derivative. Okay, so the sampling period is basically like you have here, you have a theta T, you have here theta T plus TS. Then derivative here is like the distance here is TS. Okay, the difference here is so this one is theta T plus TS minus theta T will give you this one divided by TS. That is the slope. So DDT is a slope. Okay. So by putting this one there, we are going to have T plus TS in here. Then others are just theta T. So theta T. So this is actually called difference equation. You don't have derivative there, but you have a shift one sampling period ahead. Okay. But sometimes you may say, oh, I don't like this one. I want this one to be T. Fine. Then this will be T minus TS. Okay. Everything is T minus TS. That's okay. It's same, right? Same. Depending on how you look at this. So when I do this, we are going to see this is a K, this is a T. Suppose at T, I'm already having a K times TS, a K steps already. Okay, K sampling instant already. So the T plus TS is K plus 1. Then T is K. So we just drop the TS. So these are the discrete moments. So K is 0, 1, 2, 3, right? Until forever, infinite. Okay. So yes, we can write this way, and now we can write the qk here. This is like my u, okay. This is my arrow at k. So this is proportional control, and I put this one in here. Then I'm going to get something like this. So theta k plus 1, theta k is here. You have also theta k in here. Move everything on this side, you are going to have this term. Okay, so then you have this is known, this is also known. Okay, so these are all known. Okay, coefficients. So I want to understand what is my theta k giving theta 0. Then what is my theta 1, theta 2? This is a solution. Okay, discrete sequence. Okay, so this is called the closed loop difference equation of theta. All right. So we can use the same argument, right, in this way. So we'll make a copy of this one again. So we do the same argument. What do we mean steady state? In a steady state, add one more step doesn't mean anything. So it still is a constant, it's theta SS. So I put this on theta SS in here and solve the theta SS. We can see this formula like we have seen before, okay? So we do have steady state error. It's not a perfect tracking. Looks familiar with the continuous time? Yes. So, but how we can get the sequence out? So suppose this is alpha, okay? And you move this one, is alpha here. And everything else is U bar. So this is equivalent of very simplest possible first order difference equation. Okay, so what's the general form of this one? So suppose that you start with your theta 0 as this one, and then you write theta k here as this one. So then I want to understand what's A0, what's A1, what is R, okay? So it's a function of k, function of k. But you may ask, oh, how come you can figure out this form? I don't ask. That's based on the first order difference equation. I'm going to show you a very high school level of derivation. So, so we put this one here. So we have a theta k plus 1. So I write down in here. So then I have a minus alpha theta k is here. I just add everything here. So this is my U bar. So remember, we are dealing with a theta k plus 1 minus alpha theta k is U bar. And giving theta 0, what is other points, theta 1, theta 2. So in the end, my theta k can be expressed about function of k. How we do that? So we are here. So we compare the terms. So then we know that this is a constant term. This is also constant term. So then A0 should be U bar plus alpha A0, because this is always true for any k. Okay, so I solve A0. How about A1? Okay, so A1 is here. Okay, A1 is theta 0. Okay, by setting the R is, okay, by setting the R, okay, let me say, A1 is here, okay? By setting K is, A1 is theta 0 minus A0, okay? Minus A0. Why this is so, okay? Why this is so? So for example, okay, for example, if I put in here, okay, if I put theta 0 in here, what I'm going to have, and then is k is minus 1 plus A1 R to the power of 0, right? Power of 0. So then you know what is A1. And by comparison, okay, by comparison, so this is A1 times R, R to the power of K. So then you know that A1 times R, this one, should be the same as this one. Should be alpha A1. That's why R is alpha. So just compare left and right, okay? So that's why you have this one, okay? You have this one, you have this one. So by putting R and A1, A0 put into the previous, this general form, we're going to get what we have here, okay? What do we have here? So this is a general form of your theta K. This theta K depends on the alpha, okay? That depends on the alpha, of course, depends on the alpha. If my U is constant, okay? U bar is constant. So I can write the form here. So by combining this term and this term, so you have a theta 0 alpha K. So this is due to initial condition, okay? And the other one is actually 1 minus alpha K divided by 1 minus alpha. This is nothing but this power form, okay? And this power form will remind you what, okay? It's like integrator, adds everything together, okay? So that's due to the constant input. So in the end, we are going to write small alpha, you have fast experience, okay? While alpha is this one. If you say I sample so fast, remember alpha is this, so TS goes to 0, then alpha is 1. It's not going to decay to 0, right? So sampling too fast is no good here. But sampling too slow, TS is too big, then alpha could be negative, and alpha F could be greater than 1. If something greater than 1 you to the power, then it's exploding, so it becomes unstable. So choosing a large proportional gain, okay, it will make the alpha small, okay. So it's very interesting trade-off you can see here, okay. Let's assume that when TS is 0, then alpha is 1. So you just add all the control signals together. So if it is an integrator, okay, sampling period is very short, it's kind of like an integrator, okay? Because all the stuff here is 1, okay? So it's like K, just adding them together, okay? Adding them together is unstable, right? So if K goes to infinity, then your theta K is also go to infinity, okay? That's actually bad, okay? If the sampling period is long, then your absolute value greater than 1, it will blow up to infinity as well. Blow up. Okay. So in continuous time domain, whatever gain you put there, your system is still stable. But if in the sampling case, it can be unstable. Okay. So there's a big difference between continuous time system versus sampled time system. So here we learn a little bit of lesson, taste of digital controls. So next we're going to learn something called systematic way. So we need to start with difference equation. Okay, but solving that, even when the U bar is a constant, is very difficult. But if U bar itself is not constant, that's even harder. You need a convolution, okay? Let's see. So we actually seek algebraic technique using Z transforms and with help of the pulse transfer function. Okay, so we are going to learn how to solve difference equation. If you know how to do first order, you can do high order, right? By transforming the higher order into a vector form of first order, right? So let's move on. So remember, here is no longer a constant. The control signal is time varying, it's changing. The control signal can be any form. So, but we are learning a general form of first order system with general input is no longer constant. In constant, we can add them together and pull out the U bar, you have an integrator format. But now this is different. So we need to observe it carefully. So in this case, first order continuous time differential equation. And we do a difference equation here, okay? Difference equation here. So for the room temperature control, for a tank water level control, they are all the same. And remember, we used some sort of TS, this approximation of the different discrete. This is also called discretization. So right now I use something different. I use a current KT minus KT, K minus 1 KT previous point. Because right now at T, I cannot say I get a future. This is a future. I cannot use future at present. So it doesn't make sense to use T plus TS. So remember, I prefer we use this T minus 1 T here. Well, this is our typical first order difference equation. So for the system like this or for the system like this. So then we can say, oh, we can do this is our form. One of the ideas to solve this one is called enumeration. Just list from the beginning. So let's start from 0, then you have 1, then you have 1, you got a 2, then 1 you also can express in the initial ones. So keep doing this until right to the next. So you keep doing this, you are going to see something very interesting. That is, you have a structure. So this is the same. This is simple. This is a response because of the initial condition. But this term is with some structure. I want you to observe the power of K minus 2 versus the index here. If you add them together, it will be K minus 1 always. See, 0 plus K minus 1 is K minus 1. This is 1, okay? Oh, no. This is actually is alpha to the power of 0 in here. Alpha at 0, then you have K minus 1 here, okay? So then you can construct a K, okay? Using all the previous information, okay? So let us write a compact form. Again, I want you to make sure K minus 1 minus J, this is index, plus this index will be K minus 1, right? Will be K minus 1. Because it's minus J plus the J to the alpha. Yeah. This J is from the alpha to the power of J. So then you list the J from 0, okay? Then is a UK. So beta is a constant. You can move this one in the front. So this is a compact form we are writing here. And I want you to observe this important fact. The index of alpha to the power of J and the U subindex, they add together is a constant, K minus 1. So we derived from here to here. It's a fact. And don't ask why. It's a fact. And this fact, we are going to use it, okay? Next. So I'll come back to this one, but now I was telling you that if you know how to do the first order, okay, you will be able to do high order. Let us use the second order for you. So this is a K plus 1, K and K minus 1. So this is second order, okay? Then, so I can write a vector form of X. Vector is K and K plus 1. And I can write this one, X K plus 1 could be written is alpha 1, alpha 2. You have beta in here. So in the end, you can always write, this is vector form of first order difference equation. So I use a small d difference equation. Capital D is a differential equation, okay? D is differential equation. Small d is a difference equation. So these are just matrices, but this is a vector, okay? So first order D in vector form. So in vector form. So you can always write it's comparable to this form, scalar form. And then you can always write something like this, okay? You have like a steady state, like a state space, I'm sorry. State space format, ABCD format. Okay, ABCD format. So you can try another example. Remember here I only have one U, but what if I have two U here? The same. You introduce the dynamics U inside here, and you can get the same form of this. So you can see this structure is no longer unique. There are many ways to convert a high order D to first order D in vector form. So there are non-unique ways to do that, okay? So we can iterate this thing. This is our starting point. It's a higher order differential equation, but it's a first order differential equation in the vector form. So we can do the same enumeration, okay? This is enumeration. And in the end, we come up with this same structure here. But remember, this one add this one is k minus 1. So I point out that these two add together is the maximum k minus 1 here. So this is a procedure. It's very mechanical. You can derive it using MATLAB, okay? So we can see that original difference equation in a recursive form and is based on the previous values of the states and the inputs. The equation after solving the difference equation is of another form, only on the initial conditions and all the previous values of inputs from k to k minus 1. So that is a very important observation. So in this case, given a dynamic system, we write difference equation. We can also solve this difference equation using a recursive form. If you are giving appropriate initial conditions, so we can get a step response, disturbance response, and so on and so forth. But as in the continuous time system, we don't usually directly solve the differential equation, so we use Laplace. Here, we are going to introduce Z transform to convert the difference equation into an algebraic Z transform equation. So here is the continuous time, okay? So everything is continuous time here, okay? You can use Laplace transform, you can see here. And this is the familiar control system format. But how do we deal with all those discrete sequence? We need Z transform. So I want you to remember that if I write something called x of k, you need to ask, where is the range of the k? Could be from minus infinity to positive infinity. But in reality, we probably only need to care about from 0. So this is called one-sided Z transform. It's k is from 0. K is from 0 is one-sided. So this is a definition, and also depends on whether this infinite series will converge. Okay, usually it will. You can always have example constructed that is not convergent. We don't discuss those cases, okay? Let's do some simple ones. Say, for example, I have a step sequence. So everything below 0, before 0 is 0. You can see the dots are here. So also greater than 0, then is a constant 1. So there's a 1. Okay. Laplace transform of ut is 1 over s. So this is a Laplace transformation pair. But if we have a discrete xk, then also we can get x of z according to the definition. So this is my definition. But I already told you anything below 0 is 0. Okay. Before 0 is 0. So I write down this one, then I put how to write this one. So it's actually, you should write this way. You should 1 minus 1 over z to the power of k, 1 minus 1 over z, okay? So because I know that sigma xk, k equals 0 to n, this one will give you what? 1 minus k, 1 minus x, what? N plus 1, right? Okay, n plus 1. But when this n greater than goes to infinity and x less than 1, okay, so then we can say this is just 1 over 1 minus x. In this one here is true. We can assume this is less than 1, meaning 1 over z absolute value less than 1. That means z greater than 1. So then you only have 1 over 1 minus z. So this one will give you z over z minus 1. So that is this one. So z over 1 minus z plus 1, or you should say this one, okay? This one. In other words, I know that this is called integrator. And this one is called discrete integrator. Okay, discrete. You just add past values together. Okay. So this is an example, step sequence. But what if you have exponentially decay sequence? Okay. Okay, so the same thing. You, according to the definition, then you start from 0. Then you have a divided by z to the power of k. Then you have this way. Then you have similar one. So this is actually 1 over 1 minus a divided by z. So actually you have 1 minus a divided by z to the power of k plus 1, or send k to infinity. This one is 0 when a divided by z less than 1. In other words, z should be greater than a. That's the region of convergence. Otherwise, it's not going to happen. Okay. So anyway, we ignore those region of convergence. We only assume that everything is in the region of convergence. So you got this one. Okay, got this one. So this is like. So remember, you have a e to the power of e to the power of lambda t. This actually is s plus lambda and 1. Okay. So, all right. So this is a Laplace transformation pair. Okay. So in other words, z minus a is somehow like a low pass filter ish. Okay. And of course, we can do ramp. Okay, this ramp is not that straightforward. So basically, you have k to the power of k and minus k. So you become a sequence adding together like that. Okay. So in continuous time, 1 is corresponding to this. And here you have 1 is corresponding to this. This is the integrator. But here you can see like you have 2 integrator, remember? 2 integrator. So your T is like 2 integrator. And K here, you have also square term in here. This actually can be proven by using some techniques in here. Okay. You can using elementary math to derive this form. So giving xk, you can get xz. Giving xz, you can get xk. So this is actually z transformation table, just like Laplace transformation table. So like in the inverse, so giving xz, you do this kind of integration, okay? Then you will get this one. But usually you don't go this way. You use z transformation table. Remember, we can use a lookup table, okay? So using a partial fraction expansion, you will get xz. You will get, look up at the table, you will get the xk. Okay. So we're going to practice in the homework of this week. This is the second to last homework. So we have another sensor actuator homework. Then that's all. So this is kind of messy. This is kind of messy. So I try to show you that there's a called long division. Okay, there's long division. It takes time. Let me do this. So let me delete everything here. So also everything here. So say for example, I hope you can get me f of k. So, but you are giving with this one. How to do that? There are multiple ways to do it. The first way to do is a long division. So this is your numerator, this is your denominator. So what you should do is you put the 1 in here, you're going to have 1 minus z minus 1 plus z minus 2. So then what you get is 0, this is a minus 1, z minus 1, this is a minus z minus 2. So then because of this is a minus z minus 1, I put a minus z minus 1 in here. So I'm going to get minus z minus 1, because this one times 1 is like this. Then you have positive z minus 2. Then you have negative z minus 3. You can get this one. So you eliminate this one, this minus this. So this one minus this. So you get this is 0. This is minus 2, z minus 2. This is a positive z minus 3. So you can continue. Next term is minus 2, z minus 2. So then I have a minus 2, z minus 2. Then I have positive, okay, 2z minus 3. Then I have negative 2z minus 4, okay. So I keep doing this. So I got a 0, then I have a minus 1, z minus 3. Then I have a positive 2, z minus 4. So here you know that I need to put minus 1, z minus 4, 3. Then you can continue this. So you get something like that, okay? So, so this is your F0. This is F0 is 1. F1 is minus 1, okay? This one, okay? So this is, this is F2 is minus 2, and F3 is minus 1. So keep going. Then you can draw the F. You can draw this F versus K. So you have Fk. So F0 is 1. Okay. F1 is minus 1 is here. F1 is minus 1 is here. So this F0 is 1 is this is the one. This is the point. F2 is minus 2 is here. F3 is minus 1 is here. So it's something like this. Okay. So this is called long division. Okay, you should be able to at least get the first several coefficients. This is long division, right? But there are other ways to do. It's called PFE. PFE. You have the knowledge doing a S transform. So we use existing known Z transformation pairs, find out the closed form of the inverse solution. So here, like this is a known step. This is a known exponential decay. Okay. So this is the A. Okay. Okay. So in this case, you have T is K times TS. So therefore, e to the power of A, TS to the power of K. So that is actually the coefficient, let's say lambda. So this is like lambda. Yeah. Okay. We have just learned in the previous slide. Okay. So, and there are some properties of Z transform. Like if you have a linear combination A and B constant, then it's the same. It's called linearity. But if you have time domain shifting, so this is K minus 1, it should be Z minus 1 is shifting to like this. This can be actually derived via the definition, okay? Either two-sided or one-sided, okay? So in general, if you have K minus 0 here, you have this, okay? So sometimes people call Z is a shift operator, okay? Shift operator. So, okay. So of course, we actually assume that XK and XZ is a Laplace transform, is a Z transformation pair. Then if you have a delay in here, you have Z to the power of K0. So that's a shift. So if you have a one-sided Z transform, then you probably need to take care of all those initial value problems. So we're going to give you examples, okay? So let's review in continuous time Laplace transform. So F till Fs, they are Laplace transformation pair. So the final value of F infinity, is equivalent to send S to 0 of Fs times S. Same thing is the initial value theorem. So this is FVT, final value theorem. This is IVT, right? Initial value theorem. So initial value of F0, you also you send S to infinity, you also have S times Fs. But I need to give you a warning. In Z transform, IVT, FVT is different, okay? It's different. Okay, let's see. So let's first of all, we don't consider anything less than 0, okay? So our low limit is always 0. So this is called one-sided, okay? In our quiz, I ask you to write this equation. So do it. It's called one-sided, okay? Because this is a one-sided, we are going to study the initial conditions. So of course, this is the definition. And starting from 0 to infinity. But if you do shifting here, x plus 1, then you also do x plus 1, okay? X plus 1. And you have z to the power of minus k. Because this is by definition, okay? This is by definition. So then we can write x1, x2, and so on and so forth. Then we are missing x0 here. We just add and minus, so minus z x0. So it becomes xz times z and z x0. So in other words, okay, in other words, Yes, I know that Z is a shift operator, okay? But when you do shift forward k+1, you really need to be careful regarding x0. So this is initial value problem. Recall that you have f dot, okay? You do Laplace transform of f dot, it will be s times fs minus the initial condition. So here we have the same idea of the initial condition, okay? But you also have the z in here, be careful, okay? So this is IVT. By comparison, okay, this is initial value theorem. So then what is my initial value x0? So I just put x0 in there, okay? So because giving the definition of the z transform, xz is like this, okay? Okay, so I put in the middle and I write two parts, okay? I write two parts. All right, because sending z, if I send all the z's to infinity, so this will be zeros. This also will be zeros, okay? So I send to z to infinity, then this term is zero. This term is zero. Then I only have xz left. So in other words, so simply I send this z to infinity in here, I will get my x0. So this is the star part is IVT for z transform. It's very different to, it's different. It's different to the continuous time domain, okay? You simply send z to infinity, okay? The same is true for one-sided, okay? Now let's check the final value theorem, okay? Again, we start from the definition here. Okay, so let's multiply z both sides. So then both sides, that means I shifted the k to xk+1 according to the rule, because zx plus 1 k is xk+1. Okay, so this is xk+1. So in this case, okay, I use this guy minus this guy. Left minus left, right minus right. So if the left, I have z here, and then x is here. So I insert this one here. So make sense? Makes sense. So we are going to see that, okay, we're going to see that if I send z to, if I'm going to see z to 1, so z to 1, I send z to 1, then this will be k+1 minus k. Then you keep adding. So then what's you left is the first term and last term, right? First term and the last term. So in this case, we know that the x infinity is send the z to 1, and you have z minus 1 times xz times z. So that's the way. That's the way to go. All right. Interesting. Yeah. This is especially true for the one-sided, because one-sided here is 0. This minus infinity is 0. Only here positive infinity. So again, compare this one to this one, is also different. So it's not z, it's z minus 1 times xz. Okay. So the final value theorem is different. So let's do verification. We know that the step signal. So I have initial value is 0. The x0 is 1. X infinity is also 1. So xz is here. So x0 is you send z to infinity. This is 1. X infinity is send z to 1, but you need to multiply this special term. Then it cancels out z minus 1, you get a 1. See, beautiful? Right. But what about this one? This is exponential decay. Okay. So let's try. Send z to infinity. So then this can be ignored. So it's 1. That's easy. So it's 1. Okay, it's here. It's 1. Send z to 1. Okay, and z minus 1 times this thing. So of course this is 0. This is not 0. So finally it's 0. So it goes to 0. So this is x infinity is 0. This is x0 is 1. Okay. So we verify the initial value and the final value theorem. So remember, they are both different to continuous time Laplace transform initial value and the final value theorems. Be careful, okay? So initial value is you directly send z to infinity. The final value is send z to 1. And you have z minus 1 times xz. So, well, I don't think I have time to talk about discrete convolution here. I need to use the time next time to explain to you. So next time we start from this picture, okay? We are going to study this interesting discrete convolution case. So time is up. Do you have any questions? Let's start by doing a discrete convolution next time. We have 40 students here. Again, we missed 20. So every time it's 2/3 of students attended the class. So I wish those who missed should go to the YouTube and watch the recorded lecture, okay? It's better to do synchronized way like this, okay? All right, so see you Friday office hour and class time. Don't miss, these parts are very important, okay? Very important. You don't learn this part in any other course. Bye-bye then. Take care. Bye.